temas relacionados con el nivel del mar. Lo que nos va a contar hoy son un compendio de trabajos recientes en los que ha estudiado, algunos en colaboración con nuestro grupo aquí en IMEDEA, cuál es la influencia humana sobre los cambios observados en el nivel del mar durante el siglo XX. So, please, go ahead.
Okay, muchas gracias and buenos días. Yeah, that's it. So thank you first of all for inviting me to come here to Mallorca and also to present today some of our common work. It's a work I have done mainly in the last 2 years together with Marta. And the topic today is about human fingerprints in sea level. So as a society today, we are living in a very unique climatic period. So we have seen substantial changes over the past century, and this can easily be visible when we look into global temperature. This plot here shows you a reconstruction of global temperature from Michael Mann and colleagues. It's based on proxy data of temperature. And it shows that global temperature has been mostly stable over the last 1,600 years and then started to accelerate at the end of the 19th century, showing a unique rise in the recent history of our Earth. So this shows there are unique changes in the climate system which are suggested to be related to human influences. And this period we are talking about is the period after the Industrial Revolution, often also called the Anthropocene. And these substantial changes in the climate have, of course, also influences on our oceans and on sea level. The first influence is that if the Earth warms, the ocean will warm as well. And if the ocean warms, it will expand due to changes in density. So this leads to a consequent sea level rise along the coast. The second process that happens is due to changes in the atmosphere, glacier level along the coast. And this is something we have observed at many specific sites around the world over the past century. In the more recent decades, we further see some substantial changes in the large ice sheets, which are melting increasingly over the past 2 decades and also contributing now substantially to global mean sea level rise. This unique increase or this unique change during the Anthropocene can also be seen when we look into sea level itself. There exist also proxy records for sea level. These proxy records are mainly based on sea level indicators from salt marshes. And here's one example shown from Kemp and colleagues, published in 2011 in PNAS. And these colleagues reconstructed, in this case, sea level in North Carolina, which is shown in the lower part of this plot. And you can see a very similar picture as for global surface temperature. The rates of sea level have been mostly stable over the past 2,000 years, but started then to accelerate at the end of the 19th century, showing now a substantial increase during the 20th century, which has not been observed before. There are, of course, some natural variations also in the earlier periods, for instance, in the medieval warming or during the Little Ice Age during the 17th and 18th century, but these changes were not that large as in the last 100 years. We can also have a closer look into these last 100 years and look into direct observations. When we look at sea level, the only measurement we have over the 20th century are tide gauges, and these tide gauges are located along the coastlines. These give us information how sea level has developed over the past 100 to 150 years. And in this case, shown are 3 recent reconstructions of global mean sea level from these spotty tide gauges along the tide gauges. And when you look at these different reconstructions, you see, of course, some differences between the reconstructions, but all these reconstructions suggest that there's a consensus about the rise in global mean sea level over the past century. But what is unknown so far, how much of this observed rise, which is approximately 20 centimeters. So the question arises, how much of the observed 20th century sea level rise, which is known to be unique in the recent, at least in the recent 2,000 years, how much of it is related to human influences? To get an idea about the human influence on sea level, we need so-called detection and attribution studies. And the two, detection and attribution, has a very clear definition. The detection of climate change means the statistical proof that a signal emerges from its noise. So we have natural variations in the climate system, and it may happen that we observe during a specific period a very strong change. And then we need statistics to prove whether this increase or decrease or this change is statistically significant, so whether it emerges from the background noise. The attribution part is then to determine the cause of the observed change. And this is typically done with climate models. And this is a very nice example how climate models can be used in a very useful manner. Climate models provide the possibility to look into the different forcings. They are forced with different parameters, such as volcanic forcing, solar, greenhouse gases, and all the different factors which determine our current climate. And in the climate models, we can make experiments and look what happens if we just force the climate models, for instance, with natural forcings or just with anthropogenic forcings. And such sensitivity experiments can give us then an idea how much of the observed change is related to anthropogenic causes. And this part is called the attribution. I will focus on both. My personal work was mainly related on the detection part, but I will also give some recent examples of the attribution. And I will start with the detection. Detecting climate change is a very challenging topic. The detection of external signals in climate data depends on the natural variability in the system, which can be statistically modeled. So we know that climate is very variable, it is very noisy, and in the detection part we need to find an answer whether any observed change is significantly different from what we could expect from the noise. And typically we do that with statistical tests, how the natural variability can be characterized. The most easy way to characterize climate variability is to use a white noise process. A white noise process assumes that climate variability is a completely chaotic system. There is no persistence. Everything can happen, and you see this is just one example of a white noise process, a time series. It is very noisy, but there are not very much decadal features inside. So it changes very rapidly. We know that climate is not completely stochastic. We know that in climate there are processes, dependencies, which happen. For instance, we have a kind of a persistence in the climate system. If you just go out and look on the temperature of today, one can clearly see that the temperature of today is not completely independent of the temperature yesterday or 1 week before. The climate system has an inertia, so it changes very slowly, and that introduces a kind of persistence which cannot be modeled by a white noise process. And in these cases, we need to specify more complex models, for instance, autoregressive models, which account for the autocorrelation in the system. And one example for this is shown here. This is a typical red noise example. In these cases, this is the case which is mostly used in climate sciences to prove the statistical significance. And then there is another possibility. The red noise process typically assumes that such persistence just happens on relatively short timescales. So on timescales of a few days up to a few years. But in the recent years, there has been some evidence that such persistence or dependence happens also on very long timescales of decades or even centuries. So that the climate system, the climatic changes today are not completely independent from the climate changes in the last century, for instance. And in these cases, we have to model this behavior statistically with a long-term correlated process. And the difference you can see between these different types of noise is clearly the decadal features. In the white noise, you have a lot of variance, but there are not very much decadal features. So when there's a positive change, it remains not very long in the system. In the red noise, there is some decadal variability introduced, and in the long-term correlated noise, this decadal variability becomes system. We can fit a linear trend to the observations which are shown in the upper plot. And we need now to know whether this change is statistically significant or not. If we use the simple white noise model to ask whether this trend is statistically significantly different from zero, we get some uncertainties from mathematical laws. These are shown as the dotted lines. And these uncertainties stem from the fact that if I fit a trend to a stationary data set, it may happen just due to the fact that we can have some high or low values at the end or at the beginning of the time series, that this trend is positive or negative and not zero. But the time series was assumed to be stationary. And this is tested, or this uncertainty is shown there for the white noise process for the trend. That means also that when we have this uncertainty, that the difference, so if we observe, for instance, a trend of 2 millimeters and we have an uncertainty of 0.2 millimeters, that there are 1.8 millimeters remaining, which we cannot explain by natural variability. What happens now if I use, instead of a white noise process, a red noise process? What happens is that the uncertainties increase considerably due to the fact that we can have positive or negative changes in a red noise process over much longer periods. And that means that due to the natural variability, this trend can be affected much more than in a white noise process. And the same happens in a long-term correlated process. And in a long-term correlated process, it may happen that we observe a change in the climate system, which is due to natural variability and very, very large. And that means that we have a very large uncertainty. And we need to account for this. And first, we need to check for sea level itself, whether sea level is long-term correlated or short-term correlated. Usually it is assumed in the community that it is short-term correlated. But as I will show on the next slide, this is not the truth. In a paper we have published in the last year in Geophysical Research Letters, we have asked the question whether sea level time series around the world are long-term correlated or not. And just from a physical basis, we can clearly state there must be some long-term correlations because the ocean has a very strong inertia. It changes very slowly, so there must be some long-term correlation inside. And we wanted to check that in detail. And in this plot shown are just 8 examples of tide gauge time series all around the world. And when you just look into the periods in these time series where the sea level is much higher or much lower than in other periods, suggesting that there is indeed some long-term correlation in the system. But we wanted to test this statistically and to check whether there are indeed long-term correlations in the system. We used a method which is called the trended fluctuation analysis. This analysis measures the long-term correlation in non-stationary time series. I don't want to talk too much about the details. What it does, it measures the fluctuations from one window to the next window, which is shifted over the time series. And over this, you get a so-called fluctuation function, which is shown here on the right side. And if this fluctuation function increases in the logarithmic presentation with a slope larger than 0.5, then we can assume long-term correlations. So it's a very robust method which comes from statistical physics, and it has been proven for many, many climatic time series. And here you see the results for the fluctuations functions for the 8 tide gauge time series shown on the left side. And you can, this black dotted line shows you the case of a slope of 0.5, which would mean a non-correlated process. And you can see in all cases the slope of the fluctuation function is larger than 0.5, meaning that we have long-term correlations in sea level. There is clear evidence for long-term correlations, and that means that if we want to detect any climatic signal in sea level, we need to account for the large amount of natural variability, which has to be described by a long-term correlated process. So the question now is it another one? It is further complicated because sea level itself is not a single process. Sea level is a very integrated process, so it results from many, many different processes which act on different timescales. And the question is it convenient to assume one specific noise model for such an integrated measure as sea level is? Just to give you an example, sea level itself is, as I already introduced, is affected by mass input into the ocean due to melting glaciers or ice sheets, and due to ocean warming or ocean cooling. But it is also, especially regionally, influenced, for instance, by variation in the winds, which can push the water masses from one side of the basin to another side. We have also tides in the system. The question is it convenient, if we use a time series measured from a tide gauge along the coast, to assume one specific statistical model just for this one time series? And to test this, we looked into the North Sea. The North Sea is a shallow shelf sea in northern Europe with very specific characteristics. The sea level in the North Sea is strongly influenced by winds, which push the water masses inside or out of the North Sea. And these wind effects are usually characterized by very fast processes, and wind itself is known to be very stochastic in character. So we wanted to know, is the long-term correlation which we have observed in many parts of the ocean influenced on a regional scale by such fast processes such as wind forcing? And for that, we modeled the contribution of the winds to the observed sea level changes along the coast. And these are shown here in blue. In black, you can see the observations as they are measured. And in red, you can see the differences between both. If we remove the wind effects, we get a residual, which is shown in red. And we assume that the residual just contains volumetric changes, for instance, density changes or mass changes due to glacier melting or ice sheet melting. And these are known to be much slower in character. And then you see in the lower part two plots of wavelet coherence this shows the correlation on different time scales between two time series. On the left side, you can see the coherence between the wind component and the total measurement of sea level. And on the right side, you can see the coherence between the density, the residual component containing density and mass changes, and the observation as well. And you can clearly see that the wind is mainly coherent with the observations on timescales of up to roughly 8 years, while above these periods, winds cannot explain so much variability. The residual component, which contains mass and density changes, explains a lot of variability on the sea, are very differently characterized, meaning that the winds are more short-term process, and meaning that the mass and density changes, which are mainly responsible for the observed global mean sea level rise since the late 19th century, are characterized in a different manner. So what does that mean for the characterization of the noise in terms of the detrended fluctuation analysis? Here are the fluctuation functions shown for this particular station for the observations in black, for the residuals containing the mass and the density components, and in blue the winds. And you see that when removing the winds, which have no long-term correlation, the long-term correlation in the residual increases relative to the observations directly, meaning that if we don't remove the effect, the short-term effects of winds, we cannot accurately measure the long-term memory in the climate system or in sea level. And this has results then on the statistical significance of estimating trends. And this is shown for 11 examples from the North Sea basin here. In gray, you can see the maximum natural trends. These are the trends which can just occur due to chance from statistics. And then in black, red, and blue, the trends which occur in the different components as the natural trends from the different components. And you see, when we use just the observations as they are, the natural trends, which are later the uncertainty of the observed trend, are in an order of 0.5 to 1 millimeter per year in the basin. But if we divide the time series into its different components, into the wind effects and into the residuals, we see that the sum of both, which is shown in black, shows much larger natural trends than the observations directly. And this difference is up to 0.5 millimeter per year. This means that if we now want to detect a significant trend in the North Sea in the sea level time series, the statistical uncertainty enhances by up to 0.5 millimeter when accounting for the different processes, and therefore it leads to a less strong statistical significance, and therefore to less evidence in any human fingerprint in sea level. And this is shown in the lower part of the plot. In gray, again, when we use directly the observations as they are, and then by the different colored dots for the different contributions, and in black for the sum of all contributions. And you see the external contribution detected with this technique is much lower than directly estimated from observations. We tested the same in a model framework, which gives us an overview over the entire global ocean. And this is shown in these maps. In the upper part, you're containing density changes and mass changes, and then the wind component. And then a map with the differences in the natural trends estimated from observations and from the combination of the single contributions as a sum of them. And you see that, again, we observe up to 1 millimeter per year differences between the natural trends determined directly from the observations and from the sum of all components, meaning that we have to accurately model sea level, and we have to account for the different processes. This is very important. And the largest differences occur in the Mediterranean basin and in the Arctic Ocean and in the Southern Ocean, in regions where we know that wind effects are very strong. That means that the short-term wind effects mask not only long-term changes, but also natural variations in the system, and therefore they lower. We have the reason. The result is that when we test for any significant trend in sea level, we will have an artificial high significance. And we have to account for that. And that is something we have done in the weeks here together with Marta. So we assessed different time series from all around the world, tide gauge time series. And we knew that in many, many regions there are very strong wind effects present. But we have at the moment no adequate estimation of these wind effects. So what we did was that we averaged different tide gauge time series in the different regions to so-called virtual stations. And the effect of that is that many wind effects are averaged out. So leaving only larger scale features in the time series. And then we can estimate with a higher confidence the observed trends. And these are shown here in this plot by the red line. By these box plots here. The red line shows you the trend estimate, the observed, and then the 95 and 99% confidence level around these trends. And then in blue, you can see the difference between C not be explained by natural variability, which is expressed by these confidence intervals. And you see that in most regions around the world, we can see a significant trend or a significant anthropogenic signal which emerges from natural variability. And we see some larger changes in the northern hemisphere, so for instance in the North Atlantic, and some lower changes, for instance, in the Pacific Ocean. But these are not very robust features. But the main message is, in all cases around the world, we find significant changes, at least on the 95% significance level. And if we go somewhat higher, on the 99th, we find significant changes over the 20th century in 9 out of 11 stations. We tested that approach also for global mean sea level. For global mean sea level, we tested the different reconstructions which are available at the moment, which are most popular. And for global mean sea level, we found that depending on the reconstruction which is available, which has a bit different trend, which is related to a different merging of the different time series, we find that in all cases, at least 45% of the observed change in global mean sea level is of anthropogenic origin. So this brings me to a short summary for the detection part. The detection of anthropogenic signals in sea level, which is the statistical proof, is complicated by the integrated character of sea level and the individual character of each contributor. On regional scales, high-frequency wind signals may induce biases in the detection of anthropogenic signals, and regional averaging reduces this bias and reveals significant human influences over the 20th century. Globally, at least 45% of the observed rise cannot be explained by natural variability alone. So we have now shown with a detection study that there are significant changes observed in the global ocean. The question is now, is it really climate change, or which are the factors which have introduced these massive changes? And as I introduced, before, we have to do that with climate models in which we determine the contribution by the different natural and non-natural factors in the forcing. And for temperature, for instance, this has already been done. This is just one to give you one example. In black, you can see here the observations of temperature, of global mean temperature, and then the simulation of climate models in red using all forcings. And you see the climate models do a reasonable well job in reproducing the observed changes during the 20th century. But if we just force the model with natural variations, the reconstructed global temperature curve is relatively well described up to the 1960s, but afterwards the observed trend cannot be explained by natural variations alone. And that means that anthropogenic influences are clearly responsible for the recent increase in global temperature. This is just to give you an example how it works. In sea level, so climate models have, for instance, model also the ocean. So they model temperature, and you can have salinity out of the models, but they do not model any mass changes. So the ice sheets and the glaciers are not coupled with the climate models. And therefore, in sea level, you must investigate each contribution specifically, individually, and then average them later back to the global mean sea level. And this has so far only been done for two of the main contributors to 20th century sea level rise. This is glacial melting and thermal expansion. Both contributors contributed roughly 80 to 90% over the entire 20th century to the observed global mean sea level rise. And therefore, the attribution studies which are available so far just focused on these two components. So one example is a study which has been published by Marta and her colleague in 2014 in Geophysical Research Letters. She looked into the thermospheric component of sea level, of global mean sea level in this case. And here shown in this plot are in black the observations, and in blue the forced response of all models averaged. In gray, you see all single climate models. You always have an ensemble of models of 20 to 30 models, and you assume that the average of all models gives you a good proxy of the observations. And this average of all models is shown in blue with all forcings. And in red, then the observation. No, sorry, I was wrong. In red, the observations, in black, the ensemble average of the climate models, and in blue, just the forced response. And you see it corresponds very well. So the climate models are able to reproduce the observed increase in thermospheric sea level rise quite well. And in the lower part of the plot, you can see the same as above, but just with the models having natural only forcing. And here you can see that the models are no more able to reproduce explained by natural variability alone. And in fact, Marta could show in her paper that since 1970, roughly 70% of the observed upper ocean increase is of anthropogenic origin. And at the same time, a few months later, a study from Amy Slang and colleagues also in GRL came out using a bit different method, but showing mostly exactly the same results. So we have confidence that anthropogenic forcing is the dominant factor of thermospheric sea level rise, at least over the past 50 years. Before, we cannot say very much about that component because we have no observations in the oceans. So that must be noted at this point. The authors also looked into regional patterns of thermospheric sea level rise. Again, in the upper left, you see the observations of thermospheric sea level rise. Then on the right side, you see the historical simulations by the climate models, the model average. You can see that the main features which are visible in the observations, so for instance, the large increase here in the Pacific Ocean or in the North Atlantic, are roughly featured also by the climate models. So that means that the climate models do a more or less reasonable job in reproducing the observed patterns of thermospheric sea level rise also on a regional scale. And then you see in the lower part on the left, again, the natural only run, where you see that the patterns are not no more reproduced. And then here shown is the difference between the historical and the natural only run, which corresponds then to the contribution just due to human influences, due to anthropogenic forcing. And you see indeed that in most parts of the ocean, this contribution has been positive over the past decades.
Excuse me, what do you mean by historical? Historical means that it contains
Uh,
natural and anthropogenic, but could you give some details about that model?
This is the ensemble average of all models. So these are all 21 climate models?
No, but I think what do you include? I think Aranda means
It is, for instance, volcanic forcing, the greenhouse gases are inside, the solar forcing, everything is inside. So it is the full response. And then in the natural only, you remove the greenhouse gases, for instance. And
There's a lot of privatization also to all models. No, that there's a lot of parameterization in all models, and so I guess both in the forcing and in the natural only, so there might be a lot of tuning, I guess.
I think
No?
I don't think so. They rely on the ensemble average.
okay, thank you. Summarizing, there's a clear evidence for anthropogenic forcing in the thermospheric component, at least over the last 30 to 40 years. And before, it is difficult to say something because we have no observations. The second component are the glaciers, and there has been also some progress in the recent decades. Our colleague Ben Mansayon has published a paper on that in Science, and he has reconstructed the glacier retreat over the past approximately 150 years with regional glacier models. These models are forced with the output of climate models with temperature and precipitation regionally, and he reconstructed the glacier contribution as well. And in the upper part of this plot, you can see on the right side the observations as pendadal means here in black. These are just available also from 1960 on. So he has forced his glacier models with the outputs from the global climate models. The response is shown then in red. So this is the reconstruction based on all forcings which are available, so the full historical run. And you see the observations are within the uncertainties relatively well reproduced, as for thermospheric sea level rise as well. But if you then force the glacier models just with the natural forcings, which is shown in green, you can see that we can explain the glacier mass loss over the first approximately 100 years over that period. But in the recent decades, they deviate more and more. And at the end, they cannot explain the observations very full historical model and the natural only run, and calculated statistically whether there are significant differences. And the confidence level of these differences for the recent decades for which observations are there are shown here. And you can see that when we compare observations just with the natural forcing, there are significant differences in the recent years, which go up to 100% of confidence. And when we compare the observations with the full model runs, these differences mostly disappear. There are some differences in some subperiods, but these are still relatively low. And they come from specific regions, which are explained in the paper more in more detail. But the main message from that is that we have an increasing anthropogenic contribution to the glacier melting over the entire 20th century. We have observed a considerable increase in the sea level contribution from the glaciers also at the beginning 20th century, but this was related mainly to the last little ice age, where most parts of the northern hemisphere were covered by ice. And after this little ice age, the warming in the beginning of the 20th century has resulted in an increasing glacier mass loss due to natural variations, because the little ice age was a natural variation. And then just in the later part, in the second half of the 20th century, the anthropogenic forcings dominate the observed glacier melting, meaning that the natural variability is important for the glaciers, but it cannot explain everything. And for instance, over the last period from 1990 to 2010, in that assessment, 71% of the observed glacier melting is related to anthropogenic forcing. The authors did the same analysis also on regional scales with the main melting regions. And here you see again the confidence levels of the differences between the observations and the natural only run on the right side, and observations and the full run on the left side. And again, a very similar picture. You have massive differences between observations and the natural only run, but in most cases, no significant differences between observations and the full model. There are some significant changes in some subregions, which are suggested by the authors to be mainly related to uncertainties in the observational records there. But this is an open discussion, and more discussion on that can be found in the paper from the authors. So there is a clear anthropogenic signal also in the regional response of the glaciers to anthropogenic forcing. So the summary for the attribution is that sea level is not modeled by current CMIP5 models, and observations of individual components are sparse. So from the steric, the ice sheets, and the glaciers, we have observations just over the models with full forcing are mostly consistent with the observations. And model runs with natural forcings only underestimate the observed warming as well as the observed glacier retreat. The anthropogenic causes account, therefore, for an increasing amount over the 20th century. And since 1970, roughly 87% of the observed thermospheric sea level rise is anthropogenic in origin. And since 1990, approximately 71% also of the glacier retreat is caused by anthropogenic forcing. So to come to a final conclusion, the detection of human fingerprints in sea level is hampered by the large amount of natural variability and the integrated character of sea level. The internal variability is generally smaller when averaged over large regions, and short-term wind effects may mask internal climate internal long-term variations, and we need to account for these effects and remove these redistribution effects before detecting any significant signal. Nevertheless, despite the increased uncertainties related to regional variability, we can already detect a clear human fingerprint in regional sea level and also at global scales. And globally, we can say that depending on the reconstruction we use, at least 45% of the observed global mean sea level rise cannot be explained by natural causes. And the two dominating contributors, thermospheric sea level rise and glacier melting, are both strongly influenced by anthropogenic forcing. The human fingerprints in ice sheet retreat have currently not quantified, but the ice sheets have contributed only a relatively minor part to the 20th century sea level rise, but they are more responsible for the changes in the last years. So at the end, we can say there's unambiguous evidence for human fingerprints in sea level rise. And that is it. Gracias por su atención. Preguntas.
Thank you. Any questions? It was very clear then. So if none of you have any question at all, then I think we can leave it here. Yeah. Okay. Thank you very much.
Thank you. I lost in my.
What?
Completely lost in my.
Very nice, very well organized. It was very well organized.
I felt so unclear in the detection part.
The detection? No, I think so.
I felt it was the most horrible talk I have ever been. Okay.
The microphone?
Can you help me with that? I can't see how this.